Okay, I think we can start. So it is my pleasure to introduce Professor Eli Barkai. He's a professor in physics from Bar Ilan University in Israel. So we are very pleased to have you in this talk. Thank you.
Okay, thank you very much. Yes, indeed, this is going to be a talk in physics. So if you have questions, please let me know. So what I want to present here at the beginning as some motivation is some experiment done with cold atoms in optical lattices. I will explain part of the physics, but not all the physics. These atoms are diffusing, and they are diffusing in a strange way. And this will be the topic of the talk. Actually, this is work that we did a while ago. During the conference itself, I'll present some new results. So, okay, 1 second. Yes. So I think, as you all know, this issue with fractional derivatives started a long time ago. And the meaning of fractional derivatives and integrals were of very much interest to mathematicians, starting from Leibniz. And while in mathematics, this was well developed, when it arrived in physics, at least from my point of view, this was a very confusing situation. So I want to also explain what were our problems with this field. So if we just move forward without going into the whole history, I want to point out an experimental paper by the group of Nir Davidson from the Weizmann in 2012. And they analyzed some spreading of particles that I'll soon show. And they claim, based on their experiment, that the proper way to describe this experiment is with this fractional time-space diffusion equation. So Px and T, this will be in one dimension, is the density of particles spreading in x, coordinate x at time t. This is a normalized probability density corresponding to the concentration of particles. The typical initial condition will be a kind of delta function on the origin and x equals 0, and these particles are spreading based on this equation. So of course, when beta is equal 1 and u equal 2, we have here the usual diffusion equation. So in physics, we have many questions, and the main question in this talk will be, what is the meaning of this exponent nu? How can we relate it to physical properties of the systems, that is, to the cold atoms and the optical lattice? What is this transport coefficient k nu, which is like a diffusion constant, etc.? These are the main questions of this talk. There are other questions like, what are the boundary conditions for this system? But in this talk, I'll focus on infinite systems.
Eli, may I interrupt you with a question?
Yeah, go ahead, please.
Do you mean here k nu delta nu? Do you mean here summation over nu or not? Or is this just fixed nu?
No, so the interpretation is given right here. So one way to understand these fractional derivatives is the following. This is the fractional derivative, and I go into Fourier space. So this is k absolute value to the power nu. And this is a constant which describes the spreading of the particles. And we want to find this spreading. This is like the diffusion constant, if you want. But there's no diffusion here because the diffusion is anomalous.
Yeah, but I mean, there is no summation in
No,
nu.
there's no summation. Simply the diffusion constant will depend on this index.
Okay.
There's no summation.
Thank
you. So what they did in the experiment, I'll soon explain, but they solved this equation for a delta function initial condition, and it's given essentially by a Levy distribution. And our goal is to derive this equation describing this atomic cloud, these particles that are spreading. Of course, there is much more literature on this. I point out one review in the field of physics that analyzed these type of equations, a famous review by Metzler and Klafter. So, So the main themes of my talk are, first of all, a reminder what is Levy statistics, but you know all about Levy statistics. I want to explain more what is our physical problem with Levy statistics. I want to remind you or tell you about a paradox that the physicists see, that Levy statistics, in the context of diffusion at least, is not a physical process. Then I want to show that in some sense it can still describe some experiments, but you need to know the limitations of this theory. So for that aim, I'm going to briefly describe the semi-classical theory of something called Sisyphus cooling. Sisyphus cooling is the way people in laboratories cool atoms to maybe...
Yeah, beg your pardon, just a short question. Do you know how to write asymptotic expansion for excursion of Bessel bridge?
I'm going
Imagine the Bessel bridge. Will you present the formulas?
I will present some formulas, but in the second part of the talk, we are going to discuss the area underneath the Bessel excursion and things like that. But I'm going to mainly discuss formulas with not full derivation, of course, because we don't have time.
Okay.
So I'm just explaining what are the main themes of my talk. Is first of all, what is the physical problem that we see with Levy statistics? This is related to the fact that the spreading of the packet of particles, if you believe this equation that I just showed you, it's spreading in some sense infinitely fast and violating causality. That is, as if the particles travel faster than what is permitted by laws of physics. In other words, the mean square displacement based on this description is infinite, which we think is impossible, and we know it is impossible. I'm going to discuss the semi-classical theory of Sisyphus cooling, and Sisyphus cooling is a vast field. Cohen-Tannoudji received the Nobel Prize for this method. This is the way people cool atoms in hundreds of laboratories. So this is a well-studied mechanism of cooling. And this mechanism of cooling is what is giving you the Levy statistics, the anomalous diffusion, and this strange fractional equation. I'm going to discuss this area underneath these Brownian and Bessel excursions. This is the mathematical heart of the theory, which gives you some correlations in this process that cut off the Levy statistics. And if I have time, I'm going to discuss scaling Green-Kubo. Green-Kubo is the general framework where for many years, starting actually with Einstein, people have analyzed the diffusion phenomena. And in these processes that I'm going to talk today, the usual theory of Einstein and Green and Kubo, which are related to stationarity, they all break down. So, okay, so what is the experiment? Without going into the details. So what they have here is rubidium atoms. And the rubidium atoms are interacting with laser fields. And I'm going to discuss this physics of these laser fields. And then these laser fields are the cooling mechanism. You cool with lasers, which is a little bit paradoxical at first, but this is how people manage to slow down atoms and create a very cold phases of matter. So what they do, they prepare the system in some trap, and you have here at very short time some very narrow distribution. And as time goes by, you see these atoms spread out. Eventually they spread out so much, you don't see too much, but they spread out for some time scale, for milliseconds. And then what they do in the experiment, these distribution, you see this very sharp peak, they fit this to Levy distributions. And based on that, they conclude that we have here an example in the experiment that, you know, this fractional diffusion equation is a valid description, but we want to understand a bit deeper than that, what is going on. So just to remind you and pinpoint the problem that we have with the Livy Central Limit theorem in the context of this particular diffusion process. So Livy, as you all know, considers sum of independent identically distributed random variables, which I will denote by chi I. Later, these will be Bessel excursions, but at this moment, these are just IID random variables. Usually, you have the variance of this IID random variable is finite. Then in the correct scaling limit, you get this usual Gaussian statistic. But if the variance diverges, Livy Central Limit theorem holds. And then when you rescale the sum with n to the power 1 over nu, we get this Livy statistics, Livy distribution, stable distribution. And this nu is, of course, related to the fractional exponent. For that to happen, we need a probability density function, let's say symmetric, of these summands, which folds like a power law with this nu, and this nu is somewhere between 0 and 2. And the Fourier transform of this Livy stable law, if you forget about the width, is simply given by this exponential function, k absolute value to the power nu. Now, here you see immediately a problem, and that is that the mean squared, the variance of these processes is infinite. Again, indicating that the packet, if this describes a packet, is spreading infinitely fast in the MSD sense. MSD is mean square displacement. So it's also well known, roughly in the 60s, that Mandelbrot started looking at these objects graphically, and he described them as Levy flights, let's say in 2 dimensions. So you have these type of jumps. You choose an angle at random from 0 to 2 pi, and then you jump with a power law distributed jump length, and then you get this fractal structure. However, the mean square displacement, either in the x direction or the y direction or the r direction, if it's in 2 dimensions, is infinity. And that means, and that is a problem. Why is it a problem? It means that you see, you have here one big jump. And this big jump, the time it takes in this Levy flight description, the time it takes is the same as the small guy. And this is not the small jumps. So small jumps and big jumps take 1 unit of time. And this is considered in physics non-physical. And that's why when we first saw these fractional space derivatives in diffusion equations, we kind of thought, no, this is impossible, because if you have a long jump, it will take much longer than a short jump. Very simple physics. So in this context, already in 1987, Schlesinger, West, and Klafter, they designed a very famous framework called Levy walks. In the Levy walk, what you do, it looks a little bit like this Levy flight. Because you see, you have here jump sizes which are small and jump sizes which are big. You see this fractal type of structure they are taking from a power law. However, there is a big difference, and that is there is a certain velocity. And if you have a long jump, it will take you longer time. So space and time are coupled. And what they did in the original walk, they say you move with constant speed. And then if you have the time between these turning points is random with a power law distribution, but then the longer you move, then it takes you more time. And then because you have a finite velocity, the mean square displacement is always less than time to the power 2. And this is called, again, this is called the Levy walk, and it's very different from the Levy flight. So that was a difficulty for us in looking at these type of equations, because these equations, if you believe them in free space, predict an MSD which is infinity. But still, should we throw this type of equation in the context of diffusion at least to the trash? The answer is, of course, no. But my talk is about how do you fix this problem, that the mean square displacement is infinity, but what is the meaning of this equation? So the meaning of this is the following. First of all, we need to explain what is nu, as I said before, what is k nu, but in addition, you have here this density. This equation will not be valid for very large x. There's always some cutoff due to finite speed, finite propagation, and some correlations. So this is not the whole story. It is part of the story. This is, by the way, general, not only in the context of these cold atoms. So if there are no questions, now I'm going to go into the details of the cold atom system. Okay, so what I try to hint here is that when you look at these kind of systems without these Levy flights, you need to look at not only at their position, how the packet is spreading, but you also need to look at the velocities or the momentum of the particle. And this is very important. You cannot neglect one and look at the other without understanding one another. So what we are going to start with is how does the velocity or momentum behave in this special system. So based on the theory of Sisyphus cooling, I'm going to discuss here the friction force, and it's a very strange friction force. So if you put a Brownian particle, let's say in water, and it moves faster, the faster it moves, the stronger is the friction. This is usual Stokes law. That is, the higher your velocity, the bigger is the friction. Indeed, this is trivial because when you move faster in water, you collide more with the water molecules, and then you slow down. And the friction of a Brownian particle in water is proportional to velocity or momentum. Now, this is the friction that we have here, and this will give us the fractional equation eventually. So what is this very strange friction? It's made by man, it's made by the lasers, but this friction you see here as a function of momentum. Momentum and velocity are the same. Let's say the mass is 1. You see here it's linear, like usual Stokes friction as a function of P. But then as you go to large momentum, this friction, instead of increasing with momentum, it decays like momentum to the power -1. And that means that if there is some fluctuation and you go to high velocities, then the friction is going to be not so good. It's going to be very weak. So what we have here is the following. We have here a very strong friction made by the lasers. However, this friction works in some interval between this point and that point. This is the capture velocity, never mind the details. But eventually the man-made friction is not so good. And this is the reason why eventually friction is becoming weak. And not only that, if you have a very high velocity particle, it will experience no friction at all. So at small velocities, the particle is more or less trapped, and then at very high velocities, it's more or less free in very crude way. And again, this was known by Nobel Prize winner Cohen-Tannoudji from 1991, and the connection to anomalous diffusion was pointed already in 1996 by Zoller and others. So let us go a little bit more into the details. This is a physical description without a lot of the description. So according to Dalibard and Cohen-Tannoudji, what is going on here, and why do we call it Sisyphus cooling? Again, this will be a tip of the iceberg. Don't worry if you do not understand all the details. So the idea here is the following. You have these atoms, these rubidium atoms. They have some, they are in these laser fields, and these laser fields create some electric field. This is given by this expression, which is a function of Z. And if you know a little bit of quantum mechanics, this creates some stark shift to the ground state energy of the atom. So the atom can have, in principle, 2 energy levels at the ground state, and there is also an excited state. Now, what is happening, and this is just a description, this is not a theory, is the following. This is the atom, and what it does, it goes up this hill, it then can absorb a photon, and then it will go down. Now, imagine you have a situation where you have an atom that goes up this hill, goes up here, then goes down. So clearly you lost energy by going from the top of the hill to the bottom of the hill. And this process is what is going on here, or this is the theory. The atoms go up the hill, they go up to an excited state, then they go down, they lose energy. They go up the hill, they go up here, then they lose energy, etc., etc. I'm not going into the quantum mechanics of this, but this is what is going on. I'm just telling you as a fact. But of course, like any process in physics, this is just the idealization. That is, sometimes, you know, the atom can go up here, or sometimes accidentally from the bottom of the hill, you can go to the top. So you have fluctuations. Now, maybe if you have some physical intuition, you understand why this mechanism cannot work when you are very, very fast. Because if you are extremely fast, you're going here, this is the Z, Z we'll call later X to, this is the position. Then what will happen? The atom will not be able to go up and down exactly on the maximum. So if you're extremely fast, this mechanism doesn't work. And this is related to the fact that the friction eventually decays like one over momentum. So this is the reason why Cohen-Tannoudji got this Nobel Prize on this issue, and this is why this is called Sisyphus cooling, because the atom is going up the hill, and when it reaches the top of the hill, it's pulled down. This is this name Sisyphus. So let us now just focus, however, on the math, which is, I think, maybe a bit more clearer without explaining the details. So I want to present here the momentum distribution, and this is given by a tool that I think you are all familiar with, and this is a Fokker-Planck equation. This is the density of the momentum of the particles at time t. So at this stage, I don't have position, it's just velocity or momentum. And as usual, you have the first order time derivative of the density. This is normalized to 1 as usual. You have some diffusion, and you have a friction force. So this is very common in a description, let's say, of a Langevin particle. In that case, this force will be linear in momentum. So diffusion comes here from the interaction with the laser. That is like slightly like heating, because if you didn't have friction, then it would, in momentum space, just spread. But you do have friction, but the friction, as I said before, is very strange. This is the friction force that gives you the fractional derivatives eventually. The friction force increases linearly for small momentum, like Stokes' law, like usual type of friction. But you see at very large momentum, it goes like 1 over p. Most important thing maybe is that this diffusion constant in these units, these are dimensional units, is given by this parameter. And this parameters here, this is the recoil energy. The recoil energy is after you emit a photon, how much does the atom recoil? What is the energy based on the emission of a photon? It's a well-known quantity in physics. And U0 is the height, sorry, it's the height, this height, this U0 is this thing. And importantly, this parameter, this is the dimensionless parameter. This number C is of order 10. This depends on the atom. We also know it. This is a dimensionless parameter. And the most important thing is that you can control it. You can control in the experiment U0, and then you can control D, and that will control the exponent nu in the fractional equation. And again, I want to repeat, if the momentum is high, you get very strange friction. 1 over momentum, the friction is very weak at high momentum. So why do we get 1 over 1 over velocity instead of linear in velocity? Why is this friction like this? This is a hand waving argument. So what is this friction point? You have some rate and you have some delta P. Delta P is the loss of momentum in 1 kick due to 1 emission of a photon. Now, all to prove this 1 over P law, which gives you essentially the physics here, all you need to do is usually use energy conservation. And that is the momentum of the particle after it jumped down from the hill, like Sisyphus jumped down from the hill, is P plus delta P. And before it was P. And this energy, this is the kinetic energy, has to be equal to this size of the drop, like this is U0. If you want in Sisyphus method, that will be the potential energy. Now, if the momentum is very big, then you can linearize this equation, and then the delta P is going to be inversely proportional to momentum. And that is the reason why the friction force is inverse in momentum. And again, this will give you these fractional equations. That's my claim. So this was in very short the idea of Sisyphus pulley. Let us see now, based on this momentum distribution, just what is the velocity distribution of these particles. So if I take the Fokker-Planck equation and I look at the long time limit, what I see is that the velocity distribution is given by this law. It's 1 plus p squared minus 1 over 2d. And again, d I can control in the experiment by changing u0. What you see here is that the velocity distribution for large p, it has a power law distribution. And this is important because this is the reason, one of the reasons why you have this Levy statistic is actually because the velocity itself is very broadly distributed. These go together. Now, this equilibrium density of the momentum of the speed is by itself a bit strange because, for example, if d is bigger than 1 over 3, it's very easy to put here some number bigger than 1 over 3, and then you will see that the second moment of the velocity, that means the kinetic energy is infinite, which is very strange because we know that the energy cannot be infinity. It's the same type of divergence that we encounter also in the fractional equation. If d is greater than 1, because of this 2 and this 2, there is no equilibrium distribution. And if d is greater than 1 over 5, the fourth moment diverges. So what we see here from this equation, from this very simple equation of the steady state, is that there are special values of d, 1/3, 1, 1/5, that things are, from the point of view of moments of the distribution, of the equilibrium distribution, something strange happens, things start to diverge. And these will also show up in the anomalous diffusion. These we'll find transitions. That is, the fractional equation will not be always valid. Sometimes we'll have Gaussian statistics, sometimes Levy statistics, sometimes some other things. There's a kind of phase diagram that is also controlled by these parameters, which again, this is a dimensionless parameter that is controlled by the laser field. So you can ask, what do I mean at all by, diverging second moment of momentum? First of all, this is not cold at all. This is a very hot thing. So what do you see in the experiment? So this is the average kinetic energy in units of recoil energy. And this is this parameter that I was talking about, this U0, measured in units of the recoil energy. And as I mentioned, you can change in these experiments this U0. And what you see in the experiment, you see, okay, this is the value of the kinetic energy. And then suddenly, at some critical value, boom, the kinetic energy becomes very, very big. Of course, it never becomes infinity. But this is what I was trying to show you more or less based on the equations, that there is a critical value. Here in these units is roughly close to 100 in these units. This is similar to this d greater than 1/3 in dimensionless units, where you see this divergence. And what happens here actually is that the equilibrium distribution is not the whole story. Instead, in the far tails, you must cut it off by some function of time, and then this kinetic energy is going to increase with time instead of reaching some equilibrium state. By the way, it also performs some anomalous diffusion. So this was on very shortly the momentum. I just showed you that the momentum has power laws, but now I want to focus on the position of the particle. So what do we actually do? And this is now the mathematical definition of our model. We have the velocity or momentum, and this is the Langevin equations. And it has this very strange friction force that decays like 1 over momentum for large p. And here what we have is ordinary Gaussian white noise. The mean of the noise is 0. This is delta correlated. This is totally Gaussian process in the sense that the noise is Gaussian. And what is the position of the particle? It's simply the usual definition. The x over t is equal to the momentum. The mass here is equal to 1. So I claim that from this equation, which is perfectly Gaussian, like in the sense of the noise, you can get this effective description of the fractional space derivative. And this is because of this strange friction that we are adding here. So how do we analyze this? And this is we are starting to analyze. So the basic question here is that you see this momentum and this position, there is this white noise. So these are kind of continuous, look like normal processes. What is the relation at all to jumps? We know that in Levy statistics, you sum IID random variables. How do you see here at all any type of IID random variables? So the idea is the following. This is the main idea of our analysis. Let us plot a trajectory of the velocity or momentum as a function of time, based on this equation, this simple Langevin equation that I had before. And what will this momentum do? Well, it fluctuates, and once in a while it crosses zero. So I start at zero, and then it's after some time, which I call tau 1, it crosses zero. And then after another time, it will cross again zero. And then after some time, tau 3, it will cross again zero. Now, look at this black curve. What is this black curve? You cross zero here and there. And then in between, by definition, the momentum was here negative. So if you want to know what is this displacement in this time, tau 1, you need to know the area underneath this curve. So as usual, if you have a velocity, the integral over the velocity is the jump size. So I define the waiting time between zero crossings as tau 1, tau 2, tau 3, etc. These are random variables. And I define the integral over the random excursion here as the displacement, chi 1 and chi 2 and chi 3, etc. And we are going to analyze these things. And from this, we are going to be able to solve this Langevin equation and show you the relation to Levy statistics. So chi again is the random area under the velocity excursion, and it's like a jump size.
Could you possibly show the formula for the distribution of this area? Could you be a bit more specific mathematically?
Sure.
What is the statement?
You want it now, or you want to wait a few more minutes?
Yes, I will surely wait.
You can wait. Okay, good. I want to point out some difficulties here. First of all, the zero crossings, how many do we have there in a finite time interval? The answer is infinity. So we have a regularization mechanism where we start here on some epsilon, then we cross, and then we take this epsilon to zero. I'm not going to discuss at any length. Another remark is because the Langevin equation that I showed you is a simple Markovian process, tau 1 and tau 2, tau 3, etc. are IID random variables. Similarly, chi 1 and chi 2 are independent of each other, like in the Livy Central Limit theorem. However, tau 1 and chi 1, and similarly tau 2 and chi 2 are correlated. This correlation is going to be very important because the longer it takes you to cross, the bigger is the excursion. Furthermore, there is the last guy. You measure at some time t. The last guy is going to be different than the others because the others you complete an excursion, while the last one, if you measure at some time t, you not necessarily are crossing zero. Okay, so I hope this was clear. So what is the standard approach to transport? The Einstein relation is very famous. The MSD x squared is equal to d1. 1 is here just symbolizing normal diffusion times t. And Einstein told us that d1 is equal to chi squared, this excursion squared, over tau average. So if I can calculate this chi squared and this tau average, the time between, and if both of them are finite, I can calculate the mean square displacement, at least according to Einstein. Of course, I'm not saying that calculating these two guys is easy or difficult, but in principle, this is what Einstein is telling us. Another approach to transport is given by Green-Kubo, and he says something very different. To calculate this transport coefficient, this D1, you need to calculate the velocity correlation function if it is stationary, and then integrate over it. But as we already saw, if D1, this gives you D1 is equal infinity when this D that I had in the level of the noise that I introduced previously, that was the given here by this ratio of the 1 over this optical lattice depth is given by this 1/5 that I described before. So you cannot use both these equations, which are very famous in physics, when D, for example, is bigger than 1/5. So what do we need to do? We need to take into consideration these correlations between these highs, the excursions, the random excursions, and the tiles in order to build the transport systems. So what is the general framework? We calculate these Levy walks. So the idea is these taus and these highs are correlated. That makes the problem interesting, actually. And what we have here is the problem of such sum of large number of random variables. What is the position of the particle at time t? It's the sum of these excursions, and then you have the last one where you didn't cross zero at the end, this high star, and you have this n. N is the number of crossings, which actually is infinity, again, but we can regularize with this epsilon trick. So think about n as something finite. Now, this looks like a summation of IID random variables. However, these highs and these taus are correlated, as I said before. So what is the measurement time t? The measurement time t is the sum of all these zero crossing times up till n plus tau star. And of course, n by itself is a random variable determined by the measurement time t and by the realization of these tau i's, etc. Now, we could calculate the marginal distributions of these highs and these taus. And what we showed is that the probability density function, this is kind of not so difficult to do. Actually, this was already done by Zoller, if I remember. So what one can show is the probability density function of tau is given by this power law distribution. Here you see, yes?
I'm sorry, what could be said about the joint distribution?
1 second. You are just in front of me, so be patient 1 minute. I'm going to talk about this. So the marginal PDF is given by this tau minus 3/2 minus 1/2d. D is the dimensionless parameter. This 3/2 should be familiar to I guess many of you. When D is infinity, the kind of the friction itself is like meaningless because the fluctuations are so big. And then what you get here is that the process is exactly diffusive, if you want. And then when D goes to infinity, then you have this 3/2. Now, what is nice here is that if D, our parameter of choice that is controlled by the experiment, is bigger than 1, then tau, the average time between zero crossing, is infinity. And this is exactly the same D that I told you before when the velocity distribution, the equilibrium distribution is not normalized. So D equal 1 was a special case. And of course, if the average time between crossing is infinity, then Einstein's theory, of course, cannot work. And secondly, the PDF of chi is given by this expression. And then chi square is infinity. And again, Einstein cannot work if chi square is infinity. This happens when D is greater than 1/5. And this number 1/5 also appeared. And again, you will see here that when D crosses certain limits, not only the velocity distribution has some qualitative changes, but also chi square, the average time. So physical quantities like velocity, like excursion, the variance of the excursion, the mean is of course 0, or the time between zero crossing, they all do something together. However, if we just look at this, maybe we can say if we neglect the correlations between these high i's and the tau i's, namely, let's say n is simply the measurement time divided by tau. Let's say d is less than 1, so this tau is finite. Then you see here something like summation of IID random variables or some approximation of it. And this is actually what will happen in normal diffusion. In normal diffusion, you can throw away the correlations between high I and tau I, and between this high star and tau star. And then this is like IID random variables, and then you get Gaussian statistics, you get Einstein relations, you get all these nice usual description of physics. However, in our case, this is for some choice of D, these tau and the high are correlated. So this is similar in spirit to the Levy walk. I take my computer, I generate with my Langevin equation, with the Gaussian noise, some trajectories. I look at the duration of the time between zero crossing, this is this tau, and I look at the displacement between zero crossing. And what you see here is, first of all, something which is obvious, and that is the longer the time between zero crossing, the bigger is this displacement, high. But it's not like the Levy walk. High goes like t to the power 3/2. It's not linear in tau like the Levy walk. It's a different scaling. This straight line is this tau to the power 3/2. Another exponent we have here. So how do we go about? And now I'm going to start answering the question that was asked. What do we need to analyze this type of process? We need the joint PDF of high I and tau I. These marginals are not enough. And that is the following. So I will denote the joint PDF as of high and tau as I'm using here well-known result. This is the marginal PDF, let's say, of tau times the probability density of high given tau, p high of tau. Now this one I already showed you how to calculate, or I can calculate it, but the difficult part is how to calculate the probability of high given tau. Now, from this curve, just from the numerics, but we can prove this analytically, this density function, high given tau, is scaling like t to the power 3/2. This you see from this simulation. Is there a question? Okay. So what we actually do is we find this joint PDF. If we find this joint PDF, this is just the start of the process. Then we can have the Fourier transform of it, and then we can have the Fourier transform and Laplace transform of the density of particles based on this equation. This is a famous equation in physics called the Montrol-Weiss equation. But the key here is we want to calculate this thing, and then we can more or less solve the problem. So I'll skip this. So again, the joint PDF is given by the marginal PDF, p high given tau. This is given by the scaling function. The letter B is because of something called Bessel excursions. And why is it scaling like t to the power 3/2? This is a simple argument. We are looking at large high, then P is when high is large, then there is no dissipation actually, and then P is diffusive. If it's diffusive, it goes like t to the half, and then high goes like tau to the power 3/2. And then the MSD is going to be bounded by t to the power 3. Okay, so what are these Bessel excursions? These Bessel excursions are the following. We have the momentum, and it starts at 0 and ends at 0, and in between, it's always positive. Here, I'm plotting different trajectories, and we are interested in the area underneath these random curves, and this is the average of this curve. So how do we do this? So here we have something that was also introduced by other people, Majumdar, Comte, Darling, and Bouchard, both in mathematics and physics. How do you calculate the area underneath random curves? So these gentlemen, they were focusing mainly on Brownian motion, and we are dealing with the Bessel excursion. So this chi, this is, we started with some epsilon, we add in some epsilon, this chi is actually the momentum, this is a random curve, and I want to calculate the area underneath this guy. So I'll show this, how this is done for Brownian motion, and what we do is we add the friction. I see some...
For Brownian motion, it's well known. It's a known mathematical fact for Brownian motion. For Bessel process, I guess this solves the problem.
Well, yeah, I totally agree that for mathematical, I mentioned the mathematicians of some of them just now, but we do it for the Bessel excursion. So, but I want to explain the technique we use, but I'll do it on Brownian particles, but then we generalize it to the Bessel excursion. And why do we have Bessel excursions? Again, this comes from the friction that goes like 1 over momentum, which is related to the Bessel process. So in physics, the way we do this is that we want to calculate this area underneath this random curve between some time 0 and some time t. This is, let's say, the area underneath the Brownian excursion. We map this onto a path integral approach. So we have here only the diffusive part, and then we have this constraint here, and the definition of the area, which is simply the integral over the random curve. And what is important here is that because of this definition of this functional, you get here inside this path integral, you get something linear in x. This is because we have here x. This is the momentum in our case. And this is important because this means that if you know quantum mechanics at least, this is related to something called the Airy distributions, or the solution of the Schrödinger equation for a particle in a linear force and Schrödinger equation. This is all in Laplace space. So here is what we find for the Bessel process. It's not so informative. This is the joint density of chi given tau, and it's given by an infinite sum of these hypergeometric functions. And inside we have this nu, we have this alpha, and we have also some eigenvalues. These are these lambda k's and these dk's, which are kind of properties of the eigenfunctions of some of the Fokker-Planck operator. Again, the full details are given here. I'm just going to show you the figure.
Okay. So suppose that you are not looking for the whole distribution, just for tail, for the large excursions. How could you simplify all this series to take down the asymptotic behavior?
Okay,
for large excursions.
So the decay up here is of some, I don't know why I have all these curves on me, but the decay here is very sharp. It's, I don't remember the details, but it is exponentially small. I don't remember if it's a Gaussian or Strex exponential right now. This is in our papers, but this is the distribution for different Ds. So for D equal infinity, this is what is known in mathematics. This is this Airy distribution. And this is for different Ds. These are these functions. And you see the nice scaling with 3/2. You see here the collapse of data. So this is how it looks. The most important thing from my point of view is that this thing, P chi given tau, all the moments of this object exist. That is, the fluctuations here are not very large. And actually, and now the question is, where is this function important? And this I'm going to go in. Where is this function important in the context of the density of our particles. So what we could show is that the following: if D is between 1/5 and 1, then the Levy statistics and the fractional equation describes the center part of the pocket. If D is less than 1/5, you get usual diffusion equation and then Gaussian statistics. If D is greater than 50, then we get this diverging thing. And this is because the whole approach is not valid for very large positions. So what is the message? If you are in this limit, you get Levy statistics and the fractional equation for the center part of the packet, but correlations are important, but only in the tails, when X is more or less like T⁻3/2. So to conclude, what we find is that in this regime, you get this famous fractional space derivative, as was found in the experiment, with nu given by this expression. So we were able, as I promised at the beginning, to derive the relation between the depth of the optical lattice and the recoil energy and this nu, only in a regime 1/5 and 1. It's given by this equation, beta here is equal 1, and we have this chi of nu. However, this equation cannot be abused, because if you want to look at the correlation at large X, you cannot use this equation. And what you find is the following. This will be my end slide, because I think I'm a bit late, is the following. So what I'm showing you, I'm simulating the simple Langevin equation, and I'm showing you the solution of the fractional equation. And then what happens is the following. When I scale the data, the density to T⁻⁴ that was just given now, this nu, I get this Levy stable laws. This is this black, this is this Levy curve. However, if I zoom out in the tail for large X, then I get something which is not a power law. You recall that Levy statistic decays like a power law. Instead, I get this cutoff here. You see this cutoff here, it goes down. Why is this cutoff important? Because this means that the MSD is finite. You don't have this Levy. And secondly, it means that you have two scalings for this solution. One is the famous Levy solution, and another solution is this far tail. Now you can ask me, okay, this guy is given by the Levy statistics. How do you describe this far tail? And the answer is, to describe this far tail, you need the area underneath the Bessel excursion. In fact, it's a little bit more complicated if you want to go into these rare events, because you also need the area underneath the meander. The meander is the last jump. So in short, Levy statistics describes the center part of the particle, of the density of the particles, while the excursion statistics describes the far tail. But this is only valid in the limit where D is between 1/5 and 1. And then if you go below that, you get a different phase called Richardson-Obuchov phase. I'm not going to go into this detail. Here I just flash quickly what is this diffusion constant, which we can also calculate. Okay, so I want to end here, because I think I'm over time. I just wanted to show you that this strange friction force, where we do not use any assumption of power law or jumps or anything of that kind, or we don't introduce these fractional space derivative ad hoc. Instead, we derive them from the physics of the laser cooling, from a simple Langevin equation. We showed you that the theory of Green-Kubo, of Einstein, the Gaussian central limit theorem, they all fail, but we can replace them by something new. Depending on the strength of the optical lattice, we can have either normal diffusion or Levy diffusion or Richardson diffusion. This is when correlations are very important. I did not discuss this so much. There are many unsolved problems, and here I would like to end my talk. I'm sorry that I'm a bit late.
Thank you so much. Time for more questions. Mark, you wanted to ask a question?
Okay, just one question. What is the message to take home from your talk? I try to formulate. You say agree with me or not? The problem of distribution of area under the Bessel excursion is extremely important in physics, extremely difficult, and nothing can be done rigorously so far. Yes, agree or not?
It cannot be done. I didn't understand.
Okay, first statement. The problem of studying the distribution of area under the Bessel excursion is extremely important in physics. Agreed?
Yes, I solved it, however.
Okay.
I
This
mean,
problem is extremely difficult.
I don't say it's extremely difficult. I cannot say on my own. No, I say it.
Proven on mathematical level so far.
No, I don't say it's extremely difficult because I solved it. How can I say it's extremely difficult? If I solve it, it's not difficult.
This is not a solution. This is some play with formulas. It's like it happens sometimes in physics. It's no solution. You cannot say what is the tails, how this distribution behave. What you write some series in happy geometrical function. It doesn't make much sense mathematically. It's just formal expression.
No, but in our papers we analyze this and okay. So if I go back to this figure, it depends what is interesting for you. If you look at the
large excursions, this asymptotic for large areas, asymptotic. So yes,
we analyze
some compact formula for this. It will be very similar interesting.
Yes, there is a formula for this. There are formulas for moments. There are formula for all kinds of things. It's in our papers. But the very large X's you see down here, it's this super rare event. It's not true. It's not
asymptotical formula. So how the tails of very large excursions behave. Could you show some results?
I don't know if I have it here. No, I didn't bring it with me because I admit that in physics, no one asked me this type of question, but you please contact me later. I'll directly to the references and.
Okay, thank you. Let's postpone this for the moment. Thank you.
But this is not the main message. The main message is that you can derive the fractional diffusion equation. You can find out all its behaviors, the fact that you have two scalings, there are many messages. There's not one single message. The excursions and the Bessel excursions are a tool with which we solve the correlation between the size of the jump and the time of the jump. So it's part of the story, but not the whole story.
Other questions?
Okay.
Okay, thank you for this interesting talk.
Thank you very much.
And see you next Monday for more talks.
Thank you. Bye.
Bye.